Hi guys, so today we're going to look at the graphs of quadratic equations. So what we do today is going to be very similar to what we did with absolute value. The graph is just going to look a little bit different, but we're going to follow a lot of the same processes. One of the biggest differences though with these quadratic graphs is that we're not really going to have a slope going through these points like we did for linear functions or absolute value. So to start, we're going to start the same way we did with absolute value. You're going to notice some things that are pretty similar, and you're going to see these things come up in future units as well. You're probably going to get a little sick of seeing this same chart that you will now be seeing for the third time so far. All right, so we'll start with the parent function. If you don't remember from Algebra 1 what this looks like, we'll go ahead and fill in some values. If I plug in 0, 0 squared is 0. If I plug in 1, 1 squared is 1. If I plug in 2, 2 squared is 4. If I plug in 3, 3 squared is 9. Okay, if I plug in some negative values, negative 1 squared is 1, negative 2 squared is 4, and negative 3 squared is 9. So these are all points on my graph. Now, not all of them are going to fit on the paper that I added. The 3, 9 is going to be off the graph. But hopefully you guys remember about what this graph looks like from Algebra 1. It's the shape of a parabola. The domain here is from negative infinity to infinity. Your range is from 0 to infinity. We should have a bracket on 0 because it actually touches 0. This graph is increasing from 0 to infinity, and it's decreasing from negative infinity to 0. It's positive everywhere but one place. It is not positive at 0 because when x is 0, y is 0, and 0 is not actually a positive number. This graph is not negative anywhere. You probably remember from Algebra 1 that this graph has an axis of symmetry. So if you were to draw that dotted line right there, that graph is the same on both sides of that dotted line. So on the parent function, that axis of symmetry is x equals 0. What that means, because that axis of symmetry is the y-axis, is that this is what's called an even function. And we'll talk more about that later this year. Absolute value was also an even function because of where that axis of symmetry was. But we'll get into those details later on this year. Extrema really just talk about our mins and maxes. So just like absolute value, this graph does have a vertex, which is either the highest or lowest point. In the parent function, it is the minimum. It's the absolute minimum of the graph at 0, 0. And then in behavior, remember, we look at two things. We look at as x approaches negative infinity and as x approaches positive infinity, we look at what f of x approaches. So as x's get smaller and smaller, the y's are getting bigger. As the x's get bigger and bigger, the y's are also getting bigger. So that's our parent function. Every quadratic that we're going to graph is a transformation of that function. So let's look at our transformations. And again, this is the chart that you guys are going to see over and over and over and over again. So f of x minus h, hopefully we remember it hasn't been that long, shift right. Plus h, shift left. If b is greater than 1, horizontal compression. B is in between 0 and 1. Horizontal stretch. F of negative x, reflection over the y-axis. So what this looks like in a quadratic equation. Just like with absolute value, if you remember, everything that was horizontal happened within the absolute value bars. Everything that was vertical happened outside the absolute value bars. It's going to be very similar for a quadratic, except instead of absolute value bars, we're going to have parentheses that are squared. So anything that happens on the inside there is going to be our horizontal transformations. Anything that happens outside of that squared part, that's going to be the vertical transformations. So f of x minus h will look like x minus h squared. F of x plus h will look like x plus h squared. Horizontal stretch and compression, and a reflection over the y-axis. Now, one thing you may notice, if you have a negative x in parentheses squared, that's the same thing as x squared. So what that really means is that reflection over the y doesn't really change the way your graph looks. That's one of those characteristics of this being an even function. Okay, now let's look at vertical. Okay, all the vertical shifts. Plus k, that's your shift up. Minus k is your shift down. If a is greater than 1, vertical stretch. Between 0 and 1, vertical compression. Negative out in front is a reflection over the x-axis. And all of this stuff is going to happen outside of what's squared. So the vertical changes are happening on the outside. Now, one thing that sometimes gets confused, that ax squared versus the bx squared. So notice if it's bx squared, it's actually in the parentheses. So if you were to see something like this, that would be a vertical stretch, whereas something like this would be a horizontal compression. Also, what you need to pay attention to, with absolute value, we were allowed to kind of take that number and move it. We can't do that for quadratics. It's not the same number, because if you think about it, that 2 is being squared. So we can't just move that 2 outside the parentheses. Now, if there is a number inside the parentheses, like that, we do still want to factor it out to help us find our vertex, but that's really the only thing we would need to do. All right, and then finally, if that is a negative there, that would be your reflection over the x-axis. So a negative out in front, that's what's going to make some of those parabolas that open down. All right, so your vertex is HK, okay? Very similar to what it was for absolute value, all right? Keep in mind we'll have to do the same thing. Let's say something is in this form. Let's say we have something that looks like this. Okay, before we find the x coordinate of the vertex, I can't just say it's 2 because I have this 4 that's out here, okay? So what I would need to do is rewrite this. And that can help me find my vertex. So in this case, the vertex would be 1/2, 7. Now, you're not going to see this very often with quadratics. We just don't really deal with horizontal stretches and compressions that often, but you are going to see that come up later on with some of our other graphs that we do. So it's just a good habit to get into to factor out that value. All right, so let's go ahead and do a couple examples. So to start, we're going to list our transformations. All right, so this graph has a reflection over the x-axis because of the negative. It has a vertical compression because of the 1/2. It's been shifted to the right 1, and it's been shifted up 3. Just like it was for absolute value, the right 1 and up 3 gives us our vertex. Now, here's the difference, though. Well, let's go and do axis symmetry, because that's pretty easy. Okay, axis symmetry, x equals the x coordinate of the vertex. All right, domain's also pretty easy. We'll go ahead and do that. That's going to be true for every quadratic, just like absolute value. There is nothing that is stopping your domain on these quadratics. All right, so now let's talk about the rest of the graph. Now, what we did for absolute value, if you remember, is we looked at the slope, and we just made the slope coming off that point. Well, with quadratics, we can't do that because the parent function doesn't have a consistent slope. But what we're going to do is we're going to follow the same pattern of the parent function and consider any stretches or compressions that happen. So the parent function, we'll look at how it moves in relation to the vertex. So for the parent function, the vertex was 0, 0. Then from the vertex, which in this case is 1, 3, we would go right 1 and up 1, right 2 and up 4, right 3 and up 9, right 4 and up 8. That's how we're moving from the vertex, because that's what the parent function does. What's different, though, is that this graph is not going to have the same shape as the parent function. It's been compressed and it's been reflected. So we need to take that into consideration into how we're transforming from our parent function. So typically, right 1, up 1. Well, because of that compression and reflection, that becomes negative 1/2. That becomes negative 2. That becomes negative 9 over 2. And that becomes negative 4. Because we're taking those y values and we're multiplying them by negative 1/2, because that's the vertical stretch or compression. Now, because that's in relation to our vertex, those transformations, those have already been considered. That's where we made our vertex. We just have to consider how that parent function is changing. Okay, it's not going to follow the normal parent function would go right 1, up 1, right 2, up 4 from the vertex. And then it would be the same thing on the other side because of that axis symmetry. That's what the parent function would look like. But because this graph has been compressed and this graph has been reflected, we're going to go right 1 and down 1/2 from the vertex. Right 2 and down 2 from the vertex. Right 3 and down 4.5 from the vertex. And right 4 down, that shouldn't be 8. I'm so sorry, guys. Ahead of myself. The original parent function there is 16, because 4 squared is 16, and it's going to become 8. A little bit ahead of myself, sorry. All right, so then we're going to go right 4 and down 8. Then, because again, the axis of symmetry, we're going to do the same thing on the opposite side. And that is my graph. Now, in order to have an accurate quadratic function, you need three things. You need a vertex, and you need two other points. And that's as much as you need to get your quadratic accurate. So if you want, you are able to just plot points to get those other 2 points. Personally, I like this kind of pattern graphing method, and we're going to use this, at least you'll see me use this kind of method for every parent function that we do. And that's why I like it. It stays really consistent. When we get into some more complicated graphs, plotting points can get a little bit harder, and it's easy to make mistakes. The other thing I like about this method, it makes it easier to go the opposite direction and to write the equation from the picture. All right, now let's fill in our other information. So range, bottom to top, so negative infinity, and it goes up to the highest point of 3, touches it, so it gets a bracket. This graph is increasing on this section right here. So that is from negative infinity until 1. And this graph is decreasing on the other side from 1 to infinity. All right, let's try another one. Transformations in vertex and axis symmetry. Pause the video, try and get those on your own. All right, so transformations. This has a vertical stretch. And it's gone to the left 3. So the vertex here is negative 3, 0. Axis of symmetry is x equals the x-coordinate. Domain is going to be consistent for quadratics. All right, now let's sketch our graph. So from the vertex, we're going to move the same way the parent function moves. So the parent function goes right 1 up 1, right 2 up 4, right 3 up 9, right 4 up 16, not 8 like I said last time. Then what's going to change here, okay? It's not going to look like the parent function. It's been stretched by a factor of 2. So we're going to take all of those up values and multiply them by 2, which some of these are obviously going to go way off my graph. So from the vertex, I'm going to go right 1 and up 2. From the vertex, I'm going to go right 2 and up 8. At this point, the rest will be off the graph. Do the same thing on the other side. That's what I'm saying, is I think this is a little bit faster than plotting points. It's also a little bit more accurate because you're less likely to make little math mistakes. And there's your parabola. All right, range here, lowest point is 0, continues to infinity. And behavior, we write 2 statements. As x approaches negative infinity, f of x approaches positive infinity, and as x approaches infinity, f of x also approaches infinity. Positive, negative intervals, very similar to the parent function. This graph is positive just about everywhere, except for 1 point. Okay, it is not positive when x equals negative 3, because it's 0 at that point, and that's where it's positive. This graph does not have any negative intervals. All right, so that's your basic how to graph your quadratics by transformations. Very similar to what we did with absolute value, except instead of slope, we're following that parent function pattern and considering any stretches, compressions, or reflections that may have occurred. The thing with quadratics, though, is that not every quadratic is written in that nice, easy transformation form. There's actually 3 different forms of a quadratic that we're going to look at today and tomorrow. So the one we just did, that's called the vertex form. So f of x equals a x minus h squared plus k. This is called vertex form because it's really easy to identify the vertex. So this is a really helpful form for graphing. However, what you're going to see more often, though, probably, especially when you're solving, is standard form and then root form or factored form. Standard form is in the form of ax squared plus bx plus c, which a lot of you guys probably remember using that form when you did the quadratic formula last year. Or sorry, back in Algebra 1. That was not last year. The other form is root form, or we sometimes call it factored form because it's going to look like it's factored. So you still have that a value, but you have x minus 1 root and x minus the other root. So remember the roots, those are the x-intercepts, or the zeros of that equation. That's why we like to factor to solve, because it makes it clear what your zeros are. And when you're solving, that's what you're trying to find. All right, the 2 parts of the quadratic that we usually identify, the axis of symmetry. So when it's in vertex form, that's pretty easy. It's just x equals h. But when it's in standard form, it's a little harder to find. If you remember completing the square, We're going to do this later on in this unit, but you can use completing the square to get a quadratic from standard form into vertex form. And if you remember that, that's great. And that's going to make your life a lot easier, I think, going forward. But what you also can do is you can use this little equation where you can say negative b over 2a. And that's another way that you can find where the axis of symmetry is. That's really helpful when you have standard form. Now, when you have root form, the way you can find the axis of symmetry, it's halfway in between the roots because, again, if it's symmetry, those roots are going to be equidistant from that middle point. So the vertex, again, if it's in vertex form, is hk. If it's not in vertex form and we do that negative b over 2a, to get the y-coordinate, we would just plug it in. So f of negative b over 2a. And that's how we can get our vertex. Again, to get the, if you're in root form, what we would do, again, find the halfway point of your x-intercepts. That's where the axis of symmetry is. And then plug that x value in to get the y-coordinate of the vertex. All right, so on these ones, we're not going to list the transformations because it's really hard to see the transformations unless it's in vertex form. But we're really going to do the same process, really, that we were doing. All right, so let's start with this first one. So we're going to start by finding the vertex. Well, instead of doing completing the square, because we're going to wait on that, I'm going to use that x equals negative b over 2a to find the x-coordinate of the vertex. So that's going to be negative 4 over 2 times negative 2, which is negative 4 divided by negative 4, which is 1. So the x-coordinate of the vertex is 1. All right, well, now let's find the y-coordinate of the vertex. So plug in 1. That gives me negative 2 times 1 plus 4 times 1 plus 3. So that's going to give me 5. So my vertex is 1, 5. So now, again, another reason why I kind of like that pattern method, we can do the same process in order to graph this function. Because what's nice, if you notice, that a value is what we use to adjust that pattern. That was our stretch, compression, or reflection. Well, that a is the same as this a. So if you look over here, that negative 2, this graph has been stretched by a factor of 2 and reflected over the x-axis. It's going to open down because of that negative. So we can take that same pattern from 1, 5, and we can adjust it because now we know it's being multiplied by negative 2. So from the vertex, we'll go right 1 down 2, right 2 down 8, and then right 3 down 18 is going to be off my graph. And then just do the same thing on the other side because of that axis of symmetry. Range, again, bottom to top. And then this graph is increasing on this section. And it's decreasing on the other section. All right, this next one is in root form. Okay, so remember, root form makes it really clear what your x-intercepts are. If it's been a while since you've done it, just remember it's kind of the opposite side. So if x plus 3 is a factor, negative 3 is a root. If x minus 5 is a factor, 5 is a root. The way we get that basically is if I take x plus 3 and set it equal to 0, that's what I get. If I take x minus 5 and set it equal to 0, I get x equals 5. So negative 3 and 5 are the roots of this equation. The reason we set them equal to 0 is because if one of these factors is 0, it doesn't matter what the rest of the equation is because this is all multiplied together. So if I plug in negative 3, this is going to be something different, and this is going to be something different, but anything times 0 is still 0. So if one factor is 0, the whole thing is 0. Okay, so now I have my two x-intercepts marked. Well then, let's find our axis of symmetry and the x-coordinate of our vertex. That's going to be halfway in between these 2 points. So halfway in between those points is that 1. So the axis of symmetry is that x equals 1. That means the x-coordinate of the vertex is 1. To find the y-coordinate of the vertex, plug it into the equation. So that's going to be 1/2 times 4 times negative 4. So 1/2 times negative 16 is a negative 8. And at this point, you've got 3 points. You've got 2 points in a vertex. That's enough to sketch your graph. If you want to find some other points following the parent function pattern, you're welcome to. That 1/2 is showing that compression. So if you wanted it to be a little bit more accurate, you could go right 1 up 1/2, right 2 and up 2, and right 3 up 4 1/2 and get some more points. But again, 2 points in a vertex is really all you need to draw that picture. All right, domain by now we're hopefully seeing the pattern. Range bottom to top. And then as x approaches negative infinity and as x approaches positive infinity, f of x is approaching positive infinity in both cases. Just writing it once to save some time. All right, so if you guys feel comfortable, pause the video, try these 2 on your own. All right, so on this first one, we'll go ahead and find the vertex and axis of symmetry. Negative b over 2a, so that's negative 1 over 2 times 1/4. So that's negative 1 divided by 1/2, which means it's negative 1 times 2, which means it's negative 2. All right, y coordinate, plug it in. So that's going to give us negative 3. All right, so we'll go ahead and plot that. We'll sketch our graph. We'll follow that parent function pattern. So from the vertex, all right, we're multiplying those y values by 1/4. So I'm just going to plot the whole numbers. It's a little bit easier. So I'm going to go right 2 and up 1. I'm going to go right 4 and up 4. And then I'm going to do the same thing on the other side. All right, domain, negative infinity to infinity. Range, negative 3 to infinity. Increasing. On this side, it's increasing. So that is from negative 2 to infinity, decreasing from negative infinity to negative 2. All right, root form. So my roots are x equals 1 and x equals negative 1. That means that the axis of symmetry is halfway between those, which is x equals 0, just like the parent function. That means the x coordinate of the vertex is 0. If I plug that in, then I end up with positive 2 as a vertex. And at that point, that's enough for a graph. Vertex and 2 points. Range bottom to top. And then end behavior as x approaches negative infinity, our graph is getting smaller. As x approaches positive infinity, our graph is also going towards negative infinity. All right, so that's it for graphs. Next class, we're going to do the opposite, and we are going to write the equation of these quadratics.